Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are talking about the paper machine learning, and this module is about dimensionality reduction. This is the second module on dimensionality reduction. Already in the first module we had looked at the curse of dimensionality, we had looked at the concept of dimensionality reduction, we had looked at feature reduction and feature selection, and we had seen one method of dimensionality reduction called principal component analysis. In that module I had told you that we will look at two other methods in this the next module, and that is what we are looking at in this module, two other methods of dimensionality reduction. So, these are the people responsible for the creation of this module, and the learning objectives of this module are to explain Fisher linear discriminant approach, another method of dimensionality reduction, and to understand the concept of singular value decomposition and the computation of singular value decomposition, again a mathematical technique. All the dimensionality reduction technique are basically mathematical technique based on eigenvectors. We saw principal component principal component analysis was based on eigenvector eigenvalue, and we are looking at projection, variation and scatter. Again this is a commonality between the three dimensionality reduction technique. We are looking at selecting the direction of maximum variance or maximum scatter and minimizing the correlation. Those are the two aspects or concepts of dimensionality reduction that we have already spoken about. Now let us go to the first method in this module, which is Fisher linear discriminant. Now here the concept that we are using is we want to there we try to find the line of maximum variance. Here we want to project onto a line such that the samples from different classes are well separated. Remember, in principal component analysis we did not look at classes, we just looked at the data and said that if the data would be transformed in such a way that we choose the projection line to be the line of maximum variance. So, we did not think about classification there. So, if your classification was such that it was not according to the line of maximum variance, then your classification will not be correct if you use principal component analysis. But Fisher linear discriminant actually finds projection to a line such that the samples of different classes are well separated. Okay. So, let us see examples in 2D. This is an example in 2D. And this is another. Now, if you look here, what we have done here is we have actually changed the axis of the projection. If you look in the first left hand side example, you will see that the two classes are not, if you project it onto that line there, the blue line there, the classes are not discriminated, they will come mixed. But if you project it on the blue line shown on the right hand side, you will see that the red red points are projected onto a line on one side and the green on the other side. So, there is a marked discrimination between the two classes. So, this is the concept of Fisher linear discriminant, finding such a line such that you can project it onto a line such that the classes are discriminated. So, that is a bad line to project to, and this is a good line to project to. How do we find such a line? That is what is interesting. So, this is the basis of Fisher linear discriminant. So, as you can see on the left hand side, the classes are mixed up, the right hand side classes are well separated. So, Fisher linear discriminant, our job is to find a line to project to such that the classes are well separated. So, now let us suppose we have two classes and a d-dimensional samples. Remember, our original aim was to reduce the dimensionality. So, the dimensions are x1 to xn, where there are n1 samples coming from the first class and n2 samples coming from the second class. We have, assuming there are two classes and the dimension of the data is d-dimensional data, and you have n data points, of which n1 samples come from the first class and n2 samples come from the second class. Now, we want to project these samples onto a line. Let the line direction be given by unit vector v, let us assume. Okay. So, the scalar v transform xi is the distance of projection of xi from the origin. So, you can see there you have vt, that is the projection line, and vt xt is the xi is the point there, and vt xi is the projection of the vector, distance of the projection point I from the origin. Thus, vt xi, v transform xi is the projection of xi into a one dimensional subspace. So, you can see that vector. So, you have chosen a vector v and we are choosing to project xi to that vector in such a way that the scalar vt xt, v to transform xt is the distance of the projection point xi from the origin in the new one dimensional subspace. This the projection of sample xi onto a line in direction v is given by v transform xi. How to measure the separation between projections of different classes? How do we measure the separation? So, let mu1 and mu2 be the means of projections of class 1 and class 2. So, take all the data points of class 1, project it, take all the data points of class 2, project it, and the means of those is the projections is mu1, mu2, and let that be the means of and let mu1 and mu2 be the means of the classes, not the projections. So, now mu1 minus mu2 seems like a good measure to see how to differentiate the classes. So, the mu1 is equal to 1 by n1. Please note this is the mu of the projected points. Okay. So, that is equal to 1 by n1 xi belong to C1 n1 v2 vt. This is nothing but v transform into the mean of the original points. So, that is why vt mu1. Mu1 is the mean of the original points and mu1 projection is the mean of the projected points. Similarly, you can find out for the second class and you will get v to the v transform mu2. So, you have two now you have mu1 projection and mu2 projection. So, how good is this measure of separation? The larger the difference, the better is the expected separation. So, the larger the mean, the projected mean of the two classes, the larger is the separation. That is a natural and intuitive way to talk about it. So, the vertical axis is a better line. Now, if you look here, you have projected it in such a way that you have original mu1, original mu2, that is in 2 dimensional, and then you have projected into a vertical axis and a horizontal axis. In the horizontal axis you see that the classes are mixed, they are not separated. In the vertical axis they are separated. Okay. Now, if you look here, mu1, mu2 there and mu1, mu2 here, the vertical axis is a better line than horizontal axis to project to for class separability. However, you will find that the mu2 minus mu1 is greater than mu1 minus mu2. So, the problem with this measure is that it does not consider the variance in the classes. So, the previous one, though we had the difference, we found that the better class discrimination was the vertical vector, but we got the horizontal vector to be selected because of that how the measure. That is because the measure that we used did not consider variance, because the horizontal had larger variance and the vertical had smaller variance. So, for that reason we have to consider the variance also. Okay. So, we need to normalize this difference in the projected mu's by a factor which is proportional to the variance. So, have sample z1 to zn, sample of mean is mu z is equal to 1 by 1 this, define the scatter. So, the scatter is normally I is equal to 1 to n zi minus mu z, where mu z is the mean of the points, the whole square, least mean square. The scatter is just sample variance multiplied by n. Scatter measures the same thing as variance, the spread of data around the way. What does actually variance mean? Variance means you have a mean point. What is the spread of the data about the mean point? Scatter is just on a different scale than variance, both are essentially giving you the same point. Okay. So, what you do? The Fisher solution is you normalize this difference in the projected mu's by scatter. So, let yi equal to the vector t transform xi, yi's are the projected samples. Scatter for the projected samples of class 1 is equal to this, and the scatter for the projected samples of class 2 is equal to this. This is the same thing that we did there. We got the projected samples and then we tried to find the difference between the projected sample and the mu of the projected thing, and that we got the scatter. So, for class 1 we get the scatter, class 2 we get the scatter. We find the square of the scatter, and we to normalize by both scatter of class 1 and scatter of class 2. This Fisher discriminant is to project on the line in the direction which maximizes, this is that j of v, want the projected means are far from each other. So, you have original mu1 projected mu1 minus projected mu2 the whole square divided by the scatter of the first class plus the scatter of the second class. So, we want the scatter in class 1 to be as small as possible. Samples in class 1 should cluster around the projected mean M1, and want the scatter in class 2 to be as small as possible. That is, the samples of class 2 should be around the projected mean M2. So, if it is too scattered, then the mu does not give you a good, this is intuitively correct, right. Mu gives you a good feel of the essence of the data if the scatter is small. If the scatter is too large, then that mean does not give you a good picture. So, you have to choose normalize it by using the scatter. This is Fisher linear discriminant. We find V which makes JV large, we are guaranteed that the classes are well separated. So, projected means are far from each other, mu1, mu2. So, small s1 implies that projected samples of class 1 are clustered around the mean, projected mean, we are all talking about projected, and sample small s2 implies that projected mean are scattered or clustered around the projected mean of class 2. Okay. So, all we need to know now is to express J explicitly as a function of V and maximize it. This is straightforward, but we need linear algebra and calculus. Now, what have we done? What is this J? This J of V, V is the vector that we are choosing to be projected on, is nothing but the difference between the projected means of the two classes divided or normalized by the scatter of the square of the scatter of class 1 plus the square of the scatter of class 2 in the two examples. So, now we have to express J, here we expressed it in terms of the mean and the scatter. Now, we have to express it in terms of V. So, what we do is define the separate class scatter matrix S1 and S2 for the classes 1 and 2. These measure the scatter of the original samples. So, we are doing this. This is nothing but the transformation of that is what we are taking. We are doing it. So, S1 and S2 is defined, and the class 1 has 5 samples, for example 1, 2, 2, 3, 3, 3, 4, 5, and we have just taken 5 and 6 samples. So, altogether you have 11 samples, but we are dividing into N1 and N2 and arrange the data in 2 separate matrices. So, we have just arranged it 1, 2, 2, 3 and so on 5, 5, here 1, 0 and so on 6, 5. So, we have got this. Notice that PCA performs very poorly on this data because the direction of largest variance is not helpful for the classification, this example. So, first compute the mean for each class. So, M1 mean of C1 is, just take the mean of those two, 3 and 3.6, M2 is the mean of C2, 3 and 3.2. 3.3 and 2. Compute scatter matrix S1 and S2 for each class. So, just like we did for scatter matrix 4 into, this is available again. So, you just calculate that scatter matrix. We are not going to the calculation, but you can do the calculation. Then the within class scatter. Now, what is this within class scatter? Is S1 plus S2. It has full rank, do not have to solve the eigenvalues. The inverse of SW is SW minus to the, and that is what you get here. Now, you find the optimal direction of V in this way. Okay. So, notice as long as the line has the right direction, its exact position does not matter, the direction is what we want. Last step is to compute the actual 1D vector Y. Let us do it separately for each class. Y1 is taken like this and calculated based on the actual value into the matrix that we originally had as C1 and the transpose of C1, and similarly a transpose of C2 you get Y2, and this way we have calculated the, please note you have the values that you have to project onto the vector and the other values you have to project on the vector. When you project these new values, the Y1, Y2 samples on the vector, you get on that vector, you get the class separated data points on the projection value. So, this is what you will get. So, the next, so up to now we have seen Fisher discriminant, where we took classes into consideration. We tried to project it such that the mean of the the mean between the classes is separated, but only considering the mean did not help us. So, we looked at the scatter of each of the means and then try to normalize this difference in mu's with the scatter value, so that we get a proper projection line. So, that is what we did. We mathematically went about it by finding out the covariance matrix and so on. Now, we go to the next method, which is called a single value decomposition. Single value decomposition can be viewed as a method for transforming correlated variables into a set of uncorrelated ones that better expose the various relationship among the original data items. So, if it is already correlated, it is not actually giving you much information. That is the essence that they use here. It is a method for identifying and ordering the dimensions along which data point exhibit most variation, which we saw from principal component analysis. With SVD, it is possible to find the best approximation of the original data points using fewer dimension. Hence, SVD or singular value decomposition used for data reduction. So, singular value decomposition factorizes a real or a complex matrix. So, it is done in a different method. So, for an m into n matrix A of rank R, there exists a factorization. This is mathematically available, single value decomposition SVD. A is equal to U, an m into m matrix into an m into n matrix into V is an n into n matrix. The columns of U are orthogonal eigenvectors of A transpose. Columns of V, what is V there is seen, are orthogonal eigenvectors of A transform A. Eigenvalues delta lambda 1 to lambda t of A transpose are given, are the eigenvalues of A transform A. So, and the mu is the the sigma is the square root of the lambda. So, this are the diagonal that that particular matrix is the diagonal of the what is that, ranks, okay, the rank values sigma 1 to sigma r. So, these are called as singular values. So, this is a mathematical, we have not done any machine learning here, we have just explained the concept of given a matrix A of rank R, m into n matrix, we can convert into an m into m into m into n into n into n matrix, and what are the columns of U there, what are the columns of what is that sigma, the diagonal, and the V of t, that is what we have given here. So, just to understand this, we are not going too much into detail. So, A is given here, U is given, use this, sigma is given, and V of t is given. So, sigma is that diagonal. So, and then you have these three values. So, how do you compute SVD by hand? There are a lot of tools available for computing this. So, you have to first take A and A transpose, and A and A transpose will give you U sigma, sigma transform U of t, because A transform is symmetric. So, this is nothing but mu of A, which is square root of lambda A transpose, and this A transpose of t can be written in this way. So, this is symmetric again. So, we get finally sigma of A is equal to square root of this. This is how we get that value. So, how to compute by hand? Now, let us assume we are given a matrix. This matrix is a 3 by 2 matrix. So, you can write this as W equal to A transform A, which gives you 2 2 2 2. I am not doing the calculation. Determiner of W minus lambda j is given as 2 minus lambda 2, 2 2 minus lambda equal to 0. With this I can find the lambdas, lambda 1 is 4 and lambda 2 is 0. From this I can find the sigma values, which is square root of, that is 2 and 0. Given this, I can now write V1 is equal to 1 by root 2 of 1 1 and V2 is equal to 1 by root 2 of 1 minus 1. So, given this, I can calculate U1 is equal to 1 by sigma 1 A V1 like this, and that is equal to so A, and I can calculate this, and I get 1 by root 2 1 by root 2 is U, that is U1, and given U1, U2, U3 are orthogonal bases for the null matrix. So, A transform 2 2 2. So, I get U1 and U2, U2 and U3. So, this is the final one, this is the range of A, this is the rank of A, and this is the null of A. So, this way is the computation. This is the mathematical computation. We have not done anything separately from that. We are just converting it. We are getting a different dimension. That is the idea. Okay. So, now if you have a matrix, first find the bidiagonal. This is a transformation. Then you find the diagonal or transformations. Then, so you get this, and A is a square matrix. So, you get this value. And if A is a square matrix, then mu1 is greater than or equal to mu2 is greater than mu n. So, I get A squared of F is equal to mu1 sigma 1 squared plus sigma 2 squared plus sigma r squared. So, if you take the SVD example, here m is, now this is the actually where we will apply. Here you have m is equal to 3 and n is equal to 2. So, its SVD is given by, these are the 3 matrices. What are the 3 matrices? U, sigma and the V transform. So, typically the single values are arranged in decreasing order, that is how it will be arranged. So, you have, so this is you have reduced the dimension of an m into n matrix into a n into n matrix. If A is a square symmetric matrix, then the singular values of A are absolute values of the eigenvalues of A. So, this is what sign, instead of taking sigma you can take the absolute value. If A is a square matrix, then determinant of A is I is equal to 1 to n of sigma I. So, comparing SVD and eigenvalue decomposition, both the methods that we saw up to now, that is the principal component analysis and the Fisher discriminants are different. Singular value component analysis and this, both one use SVD and the other use eigen decomposition. In SVD we use 2 different bases U and V. Here we use only one basis, the eigenvectors. Here we use orthogonal basis. Here generally it is not orthogonal. Here all matrices are possible, even rectangular. In eigen decomposition only eigen square is possible, only because only those are diagonalizable. So, in this particular module, we explained the Fisher linear discriminant approach. Now, what was the essence of Fisher discriminant approach is that it is meant as a decomposition that separates 2 classes. Now, how do we extend this to 3 classes? We have not seen. We just took 2 classes and we said that intuitively the 2 classes are separated by how far their projected means are. So, what you are doing is you are trying to find a line where the projected means are separated by a maximum. Then we found that is not always true, because the data points that you have in the projected line may be scattered about their mean. So, you must have it must be normalized by the scatter. The smaller the scatter, the better it is, the mu is representing your data points. See, the class is represented by the mu, whether it is in projected or in original. So, if it is not, if it is projected, if it is scattered, the data points is scattered about mu, then it means it is not actually being representative of the mu is not representative of the data points. So, we have to normalize this. So, the difference in mu is normalized by the scatter values of the 2 classes, and we try to find a projection line that actually discriminates between the classes. It seems an obvious answer that this would be good for classification, this type of dimensionality reduction. The next method we saw was a singular value decomposition method. This was exactly a mathematical method, we just directly applied it, where an m into n matrix is converted and brought singular value decomposition, where we use 2 bases U and V, and we use an orthogonal for doing this projection. So, with this we finished all the 3 dimensionality reduction techniques. There are other dimensionality reduction techniques also which we have not gone into. So, we just looked at 3 basic techniques: principal component analysis, where variance, largest variance was considered, Fisher linear discriminant, where we tried to choose a line that discriminates between the classes, and the third one we tried the single value decomposition, which was just a mathematical technique which reduces the dimension. So, we explained the Fisher linear discriminant approach, outline the concept of singular value decomposition. Singular value decomposition, it tries to make the concept behind it is we try to, the correlated information is made as uncorrelated as possible, because correlation does not give you too much of information, and discuss the actual computation of single value decomposition. And so, this is what we did in this module. Thank you.